So let's take a look at how an actual least squares adjustment works, or let's take a look at the process and how to set up a least squares adjustment. So least squares is necessary when there are more measurements than unknowns, or there are more equations than unknowns. And a good example of this would be to, let's say, we have 3 leveling measurements. Let's say from benchmark A, B, C to D. Let's say that A is equal to 1 foot, the benchmark elevation. B is equal to 2 feet elevation and 3 feet elevation. So we're given A, B, C, and we're given L1, or let's L2 and L3. These are the leveling measurements. L2 and L3, let's say that this is 3.1, L2 is 2.2, and L3 is 0.9. And we want to find the adjusted value of D. So how many measurements would it be necessary? What's the minimum number of measurements necessary to determine the elevation of D? Only 1 measurement would be necessary. And we have 3 measurements. So we have a redundancy of 2, which is the measured minus the number of unknowns. That's 3 minus 1 is equal to 2. So we have a redundancy of 2. So this is an overdetermined system. And if we take one measurement, let's take this measurement and this benchmark. 1 plus 3.1 is 4.1. 2 plus 2.2 is 4.2. And 3 plus 0.9 is 3.9. So we don't get a unique solution because they're all slightly different. And we want to find the least squares adjusted value of point D. So any least square setup is the following. The number of equations is equal to the number of measurements. A, B, and C are already given their benchmarks, so we already know their value. And our only measurements are these guys. And these are benchmarks. So we have 3 measurements. So we have 3 equations. So we're going to have 3 equations. The next step is to write down the measured value as a function of the unknown value. So we know we're going to have 3 measurements. And now we have to write down each measured value as a function of the unknown. And this is where many people get confused because backwards from the usual setup where we write down the unknown as a function of the measurements. So it's reverse thinking. So we have to write down L1, L2, and L3 as a function of our unknown, which is D. So in this case, how can we write down the measurement as a function of the unknown? L1 is going to be D minus A, D minus B, and D minus C. And the next step is to rearrange the equations with the knowns on one side and the unknown on the other. So we're going to have to rearrange this so that our known values are on one side and the unknowns are on the other side. So let's rearrange these three equations. So we have to rearrange it so that A plus L1 is equal to D. So these are my known values, and this is my unknown. B plus L2 is equal to D, and that's C. C plus L3 is also equal to D. Now this, obviously this is the basic setup for a elevation establishment, but sometimes it's much trickier than this, and it's always a good idea to write down the measured as a function of the unknown, not the other way around. So now we separate it into knowns and unknowns. And let's just write down the basic solution to the least squares. I guess I should have called this something else instead of A, because A is also our Jacobian matrix. Anyway, A transpose A inverse A transpose Y. Let's call this E. So let's just call this E, just not to confuse the Jacobian matrix with our benchmark. So our basic solution to the least square setup is Jacobian transpose times Jacobian inverse Jacobian transpose times Y, where Y is the vector of the knowns. That's going to be this side, so that's going to be my our Y vector. And the Jacobian is the partial derivative with respect to the unknown for each equation. The partial derivative for the unknown, partial with respect to D, is just 1, 1, 1. It's 1, 1, and 1. Partial with respect to D for this equation is just 1, 1, 1. And let's calculate our Y vector as the vector of the knowns. E is 1, so plus L1 is 4.1, 4.2, and 3.9. And then all that's left is to calculate A transpose A inverse A trans. So rearrange with knowns on one side, unknowns on the other. Then our y vector is the vector of the knowns. And then take the partial with respect to the unknowns. And then partial with respect to the unknown. And then write down the least square solution, A transpose A inverse A transpose Y. So that's going to be our final step. So I'll get rid of this here. So A transpose A inverse A transpose Y. So that's going to be A transpose is just going to be 1, 1. And 1. So that's A transpose times A, which is 1, 1, 1. This is A transpose, and that's A. And we multiply this together, 1 times 1 plus 1 times 1 plus 1 times 1 is 3. So A transpose A inverse is 1/3 times A transpose times Y, or Y vector is 4.1, 4.2, and 3.9. So A transpose times Y. So that's going to be 1 times 4.1 plus 1 times 4.2, that's 8.3, plus 1 times 3.9, that's 12.2. And what do you see over? What do we see over here? That the least squares adjusted value for a single variable is just basically the average, or 4.067. Which makes sense because it's an unweighted value, and later on we'll see how the weights actually are going to influence this. So anyway, the least squares adjusted value for a single unknown or a single variable is the same as the average. So D adjusted is 4.067. And let's calculate our residuals. Our residuals are going to be, oh, I forgot to label this. This is going to be our X, our vector of the unknowns is going to be A times X adjusted minus Y so it's going to be basically 4.067 minus 4.1 which is minus 0.003. Then X minus 4.2 is minus 0.133, and finally .167. So these are our three residuals when we substitute back our adjusted value into our equations. Because there's always, it's always implied that there's a residual. And the residual is again the difference between the measured and the adjusted. And V1 is our first residual, V2 is our second, and V3 is our third. Personally, I like to leave these out because they're just another, I guess, distraction. But if you want to include these, I mean, they can be included. But with least squares, it's always implied that there's going to be a residual, and then the sums of the squares of the residuals, V transpose times V. So take the transpose of this and multiply it by V itself. So that's going to be there it is, calculator. So 0.033 squared plus That's going to be the sums of the squares of the residuals. Square root 0.33. And obviously the sign doesn't matter since they're going to be squared. And 0.047. So that's the basic setup on how to solve a least square solution, or how to get a least square solution. Write down the measured as a function of the unknown. Write down each measurement as a function of the unknown. Rearrange so that the knowns are on one side. That's going to be the vector of the knowns. Take the partial with respect to the unknowns. That's going to be our Jacobian matrix. And then plug it back into the generic solution, A transpose A inverse A transpose Y. And then calculate the residuals to make sure that that the residuals are small. And then we can calculate the sums of the squares of the residuals.